Um, yeah. So for today's one, what is going to happen is what we talked about yesterday. If you were here, or if you're not here to the, I sent the link to the YouTube, like the session for yesterday, so you can check it out and understand what we did so far. So our whole
Okay.
goal was to build out the linked list in a way so that instead of always traversing to the end before we insert to it, we keep the tail pointer so that we can
Mm-hmm.
insert at the tail in
Yeah.
constant time.
Mm-hmm.
Yeah, and also as part of that, we are going to be keeping the size of the linked list as we add nodes, and as we remove nodes, we are going to delete the,
Increment size
so yeah,
pointer. Size
increment,
value. Okay.
increment, and then decrement when we um,
Delete.
add or delete nodes.
Okay.
So yeah, then we also saw that we needed an init method which will
Delete
initialize the list for us
list.
when we create one. Right.
Mm-hmm.
So this how we would create that, and we've also seen how to define our list structure, which is the one
Mm-hmm.
that will keep the head, the tail, and then
And
the
the tail
size.
and the size.
We
Yeah.
may add
Okay.
a few things today, but then you would only talk about a few things. So our whole goal is to ensure that when we are inserting at the tail or sorry, at the beginning or at the tail, we are getting it in constant time. The reason
Instant
why
one.
is that
Mm-hmm.
after this sessions, we are probably going to also talk about queues and stacks, and this is going to
Mm-hmm.
play a big role in that because if you don't
Yeah.
really the know-how to be able to um, insert at one place and then remove at one place
But
in
the other,
constant.
yeah, basically that's like the operation of the queues, right? It's like add
Exactly,
at the
exactly,
front, remove. Sorry, the remove from the front, add at the rear, and then you
exactly.
like move the rear pointer. So, what this project is about is like, okay, create initializing, excuse me, initializing the list, um, having a tail pointer and a size member for the list, and then when we add to the list, we move the tail pointer to the most recently added to new node basically, and then yeah, then we increment size. And so what are some of like the use cases that okay, so you mentioned queues. Okay, so that would be useful for queues, but are there like any, how do I put it, any sort of useful, like something that, when you have this kind of implementation, it's like something very very of great utility, like aside queues. I mean, queues are great, I know, but like, is there any other thing else that this could be applied to that would really make a difference? Like, I don't know if you get
Yeah, I get that. Right. So,
okay.
um, for let's say for anything that you may want to use a linked list for, this
Mm-hmm.
would be a good thing to work with. Right. So if it is not
Mm-hmm.
particularly about stacks or queues,
Mm-hmm.
right, and you constantly need to be appending to the end of the list,
Mm-hmm.
it's better to have something that allows you to insert much faster. Right. So
Okay.
based on the reason for choosing that data structure, it's better to
Mm-hmm.
have something that can help you do it in a much better and efficient way. Right. So
Mm-hmm.
if you are inserting always at the head, we don't really have to worry about the tail much like that. But if you always
Okay.
have to append to the list multiple times, right? We don't have
Mm-hmm.
to always traverse all the way to the end before we insert to the
And
end
so
of the list because that's going to be a very expensive operation when the list becomes very huge or
big.
very large.
Yeah.
So
Okay.
um, there are so many use cases of linked list and other data structures even use it to do what they need to even do. Right? Like other
Mm,
data structures like depend on this. For example, like the stack and the queue, other
yeah.
binary is also sort of also work with these things, right? So like
Okay, sorry,
let
could you like walk me through how the binary trees work with this implementation? So maybe full disclosure, I don't know how binary trees fully operate. I just have like a mild, understanding about it. But if I let me just say what I know. So basically, you have like a starting node, and then that links to two other nodes, and then those link to two others, and then two others like that down the line. So I don't know if I'm right or wrong, but maybe you can like just clarify that. Then you said this implementation helps in maintaining or like writing algorithms for binary trees. So first things first, what are some of the particular use cases for binary trees? Then how what are some of the operations that makes this implementation useful for binary trees based on the operations that can be performed on them as two, and then what are the like what are some of like the drawbacks of using this with like to implement a binary tree? So
all
what
right.
are binary
So
trees? Yeah.
okay, so like I wouldn't really want to go into that because like there's like we would want to focus on this one at the moment. But then, like when we discuss binary trees, I think we can go more into that. But
Okay.
binary trees
Okay.
are useful for search algorithms, for sorting, for file systems. Like they have a lot of cases, right? So if you can think of anything that has a hierarchy, you can
Okay.
think of it in kind of those kind of things, right? So
Mm,
just that maybe we may not really be able to go into it that much, but then it's really useful in multiple cases, right? But for
okay.
now, trying to narrow in on this one, and let's say
Okay.
maybe the time comes and we have to talk about it. Well, we can handle that much
All right. All right.
easier.
That's fine.
Like useful for a lot of things, like a lot of stuff, right? Like a few that I mentioned for sorting, um, searching,
Section.
a few
Okay.
things, right? So,
Okay.
for example, in Python, when they are talking about their inheritance stuff, when you really think about it, you see it has something to do with binary trees, but users don't
Mm,
really talk about it very much, just
okay.
not to make um,
So,
like
so we can
to
like
give it
focus.
at
Yeah.
this point. Yeah,
Okay.
yeah. So
All right.
yeah, yeah. But there's a lot to actually talk about that. But a good understanding of linked lists will eventually propel us to that area where we understand it better.
All
Okay,
right.
so this was our goal, or this is our goal, and then we came up with the um, the codes that we needed for the first ones, right? So we got the structure set up as well as the linked list structure as well. And we said we would use these two macros to get the first and last nodes in the linked list, right? Also, we have the init function and the append, right? So I added this node over here just so that I can add the push method so that at least we have something that's going to be inserting at the head of the linked list. All right.
Okay.
So this will just be a variant of the append, right? So it will
Mm-hmm.
just push data to the head of the list.
Okay.
So
Okay.
now that I've done that, I think I can just get rid of this to do. Right. So that's what we have here. And we would also have to work with a few other things. But for now, let's just really concentrate on this one. Our purpose is to see how we can use the head and the tail. Everything else you know about linked lists when it comes to inserting at a particular index, which requires us to traverse, is not really our focus for now. We are really concentrated on the inserting at the head and the beginning. Right? We would talk about inserting somewhere within the list maybe another time. But then this is to show that when we use the head and the tail, we can insert at the beginning and at the end with very minimal traversals or none at all. So yesterday we built out the init function and then also the print list function. But one more thing that I think I wanted to fix here is this here, that when we are printing element at something like the function here, and then the the prototype doesn't really match well. So I wanted to change this to make it
Index,
index.
right? Okay. Yeah, I
Yeah.
was
So,
thinking about it.
yeah. So now inside of this function or inside of this file, we would like to create the other operations which we would use. So I'll probably come to the end of this place, and then what I want to add now is the, let's say, the push method, right, which is going to be something that is very simple so far. So the push method, as we know it, it's to insert at the beginning of the linked list, right? So if we have something like the push method over here, right? So using the same linked list that we have, if we are to use the push method, we know that what will happen is that it will essentially insert at the beginning of the linked list, basically adjusting the head to point to the new node. So let's say we have this new node somewhere here. Yeah, okay. So this one over here also has maybe an artistic use, because at least it is also making us see that linked lists are really scattered across in memory. Right? So let's see that, and then here the next pointer is now, because we don't know what is there yet, or like
Okay.
it's nothing yet. So now we would have to make sure that we are inserting into the head or inserting at the beginning. And normally what we know is we already have the head pointer. So all that we do, first of all, is that we will set the new node's next pointer to the current head, right? And the current head points to this guy, right? Then once we are done with that, we just say that, okay, now the head is this guy.
It's the other guy. Okay.
Right. Yeah. So now what we have to do is to get rid of this, and we are left with also changing the address of this so that we can point to the correct place. So here, let's say this address was 350. Let's just say that. All right. So now
Head is
our head
350.
this. All right. So this is our new head. Okay. So if we need to insert another head, let's say another head, for instance, or like another node that would, let's say, be around this place, has data field of probably -5. Its next, we don't know. All right. So in the same way, we set the next of the head to sorry, and then the head to the new node, right? So this same thing also applies here. So we just say the next pointer of this over here. Let me change the color for this sake. So this here would point to this, and then now the head points to that. Right. At the end of this, what we do is we would also get rid of this,
Yeah.
and then as a final step, we would have to set
350.
our next pointer to that, right? Like our address field to that, right? So maybe you are used to seeing the linked list done in a linear fashion, but it's really not linear. And I hope this is making it clear like that. It is just scattered across. Okay, and this is because of space, but I think it's also adding some artistic effect, which is okay. So now we understand that this basically what we are doing. We just
Okay,
we
sorry,
are just
sorry,
essentially doing the same.
sorry for interrupting. Just to clarify,
Yeah,
right? So it basically means that the way the next element in an array is like the data type, like is a, if it's like an integer data type array, the next element in the array is like 4 bytes, or yeah, 4 bytes for an int data type. That's not applicable here. It's like any address. The addresses don't have to like be numerically symmetric based on like the distance between them, right? It could
yeah,
be
and you see that there's already a size for a pointer on a
mm-hmm,
64-bit machine. It's 8-bit, sorry,
eight
8 bytes.
8 bytes. Okay.
Right. Yeah. So so long as you're able to point this to the location of where this byte, this address is, which is also 8 bytes, that's
Mm-hmm.
all we need. And whatever data is inside of it, that's what we would grab. Right. So
All right.
in other languages like Python, where the data field can be any data type at all, like
Mm.
the data type here doesn't really like or let's say restrain us on what we can put there, right? But in C or when we are starting out, we just try to make it simple by using numbers. But we could
Yeah.
actually make sure that maybe the data type we are using is dynamic, right? But
Okay.
for this one, it's just keeping it much simple by using just an integer, right? But then it
Okay.
doesn't mean that we can only keep integers. We can be heterogeneous in what we put here. But currently, we are
Mm.
just being what we would say homogeneous, but just saying that putting just one data type there, right? So
Okay.
yeah,
Yeah.
that's what we have there. Okay,
All right.
okay. So essentially, what we are doing is let's say inserting at the beginning. Right? Basically, what we do first of all is we set the next pointer of the new node. Uh, okay, let me try to bring this here a little bit. Probably have to create a different buffer. Okay, probably this can shift to this side, which so we've seen a few things already. So to
Mm.
insert to that, we set the next pointer of the new node to the current head, right?
Mm-hmm.
Then set the
The
head
head
to the
to the new
new node.
node.
Okay. And that's basically what we've been doing, right? So
Mm.
um, that's that with this one here. All right. So let me put that into let's say a div. Okay,
Mm.
so yeah, we have that. So now let's put this same thing back into code, right? So here, first of all, what we need to do is to create a node, right? And I don't have a function that will create a node and return it. I actually find that one very repetitive because anyway. So let's go ahead and then create our thing. So here we do node t because we are creating a node. Right? So node t, I'll call it new node. And then what is going to happen is this, is we set new node, let's say equal to malloc, size of the node t, because that's what we are going to work with. Then we would check for any unexpected behavior. So if new node equal to now, that means an error occurred. We probably just print fprintf to the standard error to see that error malloc failed. Right? So when malloc fails, we probably wouldn't want to like exit out. We will let them know that they can't like insert anything more. Okay, so we wouldn't like bail out on them, right? If we
Mm-hmm.
want to exit out of this at this particular point, then we have to also have a function that will clean up everything before we leave here. But for now, let's just say that when malloc fails, we wouldn't insert anything. So let's just work with that. So let's just make it a bit more descriptive. So
And they might want to even like print stuff if even if they can't add stuff to it. So you might want to like display the list. It doesn't necessarily mean that like if you can't add to the list, you can't do any other thing. So this makes sense. Yeah.
yeah, yeah. So now when everything is okay, so that just as we said, the first step is we set the next pointer of the node to the current head, which in our case is stored in the list. That right. So we have
A pointer to the
this,
list.
yeah. So then we are getting the head member
Head
of the list,
member of it.
right?
Okay.
So then what we do is we set the head to the new node, right? And that's everything that we will do. And as part of what we said we will do, we have to increment the size,
Size.
right?
Yeah.
So we have done that and everything is okay. So here I'll just add some here. So increment size of the linked list or increment. Okay. I think it's descriptive.
Yeah.
Yeah. So that's everything that we need to do for this function here, right? For the push function, we just insert at the beginning of the list, and we are okay, right? So
Hmm.
as
Sorry,
yeah,
just a moment. The data part, we are yet to put it in the new nodes.
exactly, true. Yes, yes. So thank you. So new
Yeah.
node data is equal to the data. Yeah, thank you for mentioning that. As well, we should also make sure that we are checking for any kind of error that can pop up, right? Sometimes maybe they call the push function without initializing the list,
Ah,
right? So when that is not initialized, we would have to check that. So most of the time, I always say that like it's not a good thing to like immediately create the new node and malloc something, right? So let's check for that first before we even malloc anything. So we check if the list is equal to now, then you printf and then say that the list is not initialized. So once we have that, then we would return from there, right? So here, it's not like there's a row error that we have to exit out, right? So they've not initialized the list. We want to still give them a chance to initialize the list and then come again, right? So probably maybe this might be used in a let's say an interactive place where they are trying to work with us. So if the list is not there, we don't want to exit out of their whole program. We just want to give them control back to like give control back to them so that they can do what they have to do, right? So yeah, we are just checking for let's say ensure the list is initialized. Right. So that's what we are going to do here to ensure that it is initialized. So if it is not, we don't even create the new node to begin with. Right. So but then if it is initialized, then we can go ahead and then do that. Right. So now that we have this, we can also go ahead and then create our append function. And I'm always tempted to say method coming from a Python background. So yeah, so anyway, method functions, they are the same people, just the context is where yeah, and sometimes it can lead to a lot of arguments. But anyway, that's what it is. So, with our append method, that's what we discussed
No,
yesterday,
but
where
the arguments for functions and the methods is not as pointless as the argument of tabs and spaces or like Emacs and Vim, I guess.
yeah,
There's
but
more
like
like contextual, or semantic value to the argument of functions and methods. Like, you can't say that there's nothing like methods in C, like in non-object oriented programs, but like I don't know, let's not get into the the semantics
Yeah,
now, just on a lighter note.
yeah. Okay. So coming back to this place, normally when we were keeping only the head node or the head pointer, we would have had to traverse all the way from the beginning of this list, which is the beginning over here. Then we get to the next pointer, which is to this, get to the next,
Mm.
the next, to the next, before we can insert at the end of the list. But since we have the tail pointer, we already know that it is pointing directly to this last node, which is
Last
this guy
one.
here. So if you
Yeah.
have a new node which we have to insert, let's say a new node, oops, we have a new node that needs to be inserted over
Mm-hmm.
here. We don't know the next yet, so it's now. And then let's say this one has negative 34, right? So here, all that we need to do is similar to working with the inserting at the beginning. Is really very similar to that, right? All that we do first of all is to say that now the tails next is going to
Mm.
point to the new node,
New node. Okay.
and really that is everything that we need to do. And then everything else is to just point the tail to the new node.
Mm.
It's very similar to when we are inserting at the beginning. We
Mm.
set the next pointer of the new node to the current head. Here we are setting the current sorry the next node of the tail node to the new node. It's just a little bit different, and then we set the tail to the new node, right? So that's like the small difference that we have here. So now here we would also have to set the address part. Let's say this one over here was address 650. Right?
Mm.
So here the address part is going to be 650, and then this guy here is pointing to nothing, or like that's the end of it, right? So you can see that this is really just going up in the way that it would not normally do. We are not traversing to the end of the list before we do that, right? So now I would also like to put that into words. So let's put it here. So to insert at the end of the list. Okay, I think, oops. Oops, sorry. Okay. Have I done something silly? Oh, I did. Oh, yes, I did. Let me just see how many times I did that.
Okay, that's the last one.
Yeah, I think so. Yes. Okay. So so when we are inserting at the end, we set the next pointer of
Of
the
the
tail
tail.
to the new node, and then we set the tail to the new node. Right. So
Mm.
that's basically what we are doing here. We are just moving things around in constant time, right?
Mm-hmm.
It didn't matter the size of the data or the size of the list. We just did it in a finite amount of steps. So now also there's also going to be the same thing here where we are going to do about the same thing. You do node T, new node. Yeah. And there's one more thing that I like to mention, right? When the list is empty, we saw that yesterday, right? When the list is empty, right? Let's say I'll come back here for, or I'll go back to the board, like the other part soon. So when the list is empty, right? So at that moment, the head and the tail are all pointing to nothing, right? They all will be now in the beginning, right? here would also be now, right? So they'll be pointing to nothing, right? So let's say that we have a new node that comes inside, right? So in this particular case, the head is going to point to the new node. The tail is also going to point to the new node because that's the very first node that entered the list, right? So for the very first time, the head and then the tail are going to point to the same node because that's the beginning of everything, right? So that's something that I wanted to mention, which is going to be part of what we are trying to do here. Okay, so now let's get back to our code environment. Here as well, we'll check if the list is empty, right? And I can see that I'm doing something and I'm copying it, which I don't like. But for now, let's just keep it that way. But we could have written a function to keep this like nicely. But for now, let's just keep it in blue, right? So our new node is equal to malloc, and then we would set up that. And I can see myself doing the same thing again. So it's really just like this function is just like this. But okay, for now, let me just write everything out just so that we can use that as a learning something. So new node is equal to malloc, the size of node C, right? And then we check if new node is equal to now, then we will print out an error message. For this one, I'll copy. Right. So we can see that every time we are checking for that, we are constantly doing something over and over again. And I think for now we will leave it this way, and another time we can see how to like break functions or snippets of code that occur multiple times into a specific function, like how you
Yeah,
can identify and then
I
build
was I
those.
was I was going to actually bring that up, but I wanted you to like land first. So like when you mentioned the fact that you really don't like repeating what you have done once already, and it's like I feel like I share your sentiments completely because, but the fact that I share your sentiments doesn't mean I'm as good as you at doing something about it. So like when you want to modularize now, like I know there are some things that one has to consider, like okay, the inputs to the function, the outputs of the function. Like for instance, this push function now, right? So we have that condition: if list equals null, fprintf, and then return. So if we have a function that is implementing those lines of code, like that 5 lines of code, the function itself is going to return, and then when it returns, it's basically you are going to have to like return that function from this function. So it's like return the call of the function. But sometimes it's not that easy. Sometimes it's like there's just a couple of things that play into it. For instance, if there needs to be like a particular parameter or a value that must be passed to the if statement. Let's just assume if there's a value that must go into the block of code, sometimes it gets like very confusing or like hazy when trying to
Mm.
like do stuff like that. So maybe when were dealing with that, I definitely have like a lot of questions on that. When we're
Yeah,
doing that, it would be very useful. So yeah,
yeah.
I'm
So
done.
yeah, for now, I'll just leave it just as it is so that we can still
Mhm.
keep it to this one. Okay.
All right.
So now coming back to this code here, we said that we would set the tails next, right? Oh, okay. I'm always very like rushing to get that working. So I'll say the new node data is equal to the data. And then what we do now is that we would set, we would have to check two cases, right? So we would have to check if the list size is equal to 0, right? And you see, now we are able to sort of say it in a more clearer way, right? Because now we are not saying if the list head is now, right? Here we can say if the list size is 0, right? So if the size is 0, that means that there's nothing yet in the list.
In the list, yeah.
Yes. So if that is the case, then what is going to happen is that the lists head
Mm.
going to be equal to the new node, and then the list
Okay.
tail is also going to be equal to
Into the new
the
node.
new node.
Mm.
You know, right? Yeah.
Mm-hmm.
Else, what is going to happen is that we are just going to adjust the tail
Add this
pointer,
in. Okay.
tail pointers next equal
Okay.
to the new node,
New
and
node.
then the list tail now
Will.
to adjust the tail to point to the new node. Right.
Mm.
Then as our final step, we would have to increment the size of
Mm.
this one. Yeah.
Yeah. Okay.
Yeah. So that is what we can do. Okay, I left the semicolon here. Okay. So this is like on like some operations that we can perform with that. You can see that normally what we would have done was to do while temp is like temp next is not equal to now. Then we set
Mm.
temp next temp equal to temp next
Ah,
point to the new,
yes. I know, right?
right. Yeah. So here now what we are doing is doing this in just one step. We don't traverse. Oops. We don't let loop through the linked list from the head to the end before we find that. We already know the tail, right? And
Mm.
the other important thing is making sure that we are setting the tail after we adjust it or we insert
Mm.
anything there, right? So
Yeah,
now
to
the
keep track of
other
it.
important thing we have to do is to always do this. Like the new nodes next has to be set to now
No. Mm.
because we are inserting at the end. So I think that's one more thing that I will have to add here. Uh, Let me bring it up a little bit. So set, I think this one would actually have to be 2 and here will be 3. So set the new nodes. The new nodes, I can't spell. New nodes next pointer now. All right. So that's what we are going to do. All right. So that will be that. So now we have implemented the push and then the append. See whether they are really working as we expect them to work. So we are going to write some code to work with this, right? So
Mm.
here I was suggesting that we can use the size member to rather check for like when the list is empty, because I was using if list is now and then that is that, right? But
Mm.
yeah, but actually here I was also thinking of putting this into like specific checks, right? Because if the list is now, that means it has not been initialized. But if
Yeah.
the list head is now, that means the list is empty. So since we are here, let's just copy this. And you can see we are still copying and
Mm.
pasting. We would we would have to come back here and then fix that. But for now, this is the best solution we have. The best of all of them. Right. So since I'm getting rid of this now,
You can now use the size.
yes. So
Okay.
I can say if the size is equal to 0.
Of 0.
So now
Okay.
we've been able to catch both cases well, right? So if the
Yeah.
list is now, it is because it is not initialized, not because the list is empty,
Empty.
right?
Mm.
Yeah.
Mm-hmm.
So if also the list is initialized but then not populated with anything, then it is empty, right? So
Empty.
now we
Okay.
are getting back useful feedback for different cases. Okay.
Yeah.
So now let's work on let's say writing a driver code for this. So driver.c, and then let's work with that. So here I'll include the lists.h. Then here we can have our main function, void, and then what I'll do is I'll just say that list t, right? We are going to create a list. So my list, well, let's just say call it a list, is equal to init. Remember that we said that we use the init method to initialize the list. So that's the first thing that we do. So now you check if list is equal to now. Oh, and actually, here's what is going to happen. In the init method, in the whatever, in the init function, when an error occurs or when it is not able to get it right, let's say if malloc fails, we exit out of it. So here we don't really need to check if it failed, because if it failed, we wouldn't even be able to have access to this to do anything else. It will exit out immediately. But maybe we can change that at another time if maybe the people that will be using this function would require that we don't exit out. That's fine. But for now, we exit out, right? So now what we are going to do is we are going to, let's say, push to the list. Let's see whether everything we've done so far is correct. So that, and then let's say we are inserting. Okay, so because of laziness, right? Let's just have a numbers array, which we would create a macro for it of size 10, so that we can use that size. So size, and then that's going to be equal to, let's say, some random details. Let's see, 10, 4, 5, 4, 1, 67. How many do I have even at this point? This is 1, 2, 3, 4, 5, 6, 8. So we need 2 more.
The rest are just 0.
Okay, yes, 0. Okay, so I need to give it the data type we are working with, and then now let's go ahead and then just do something. So now you would rather do this within a for loop. So for I equal to 0, I is less than the size, I plus plus. Then within this place, we are going to insert the numbers I. Right. So that will be what we will do. And then right after we do that, we will print out, print the list like that. Right. So now okay. So now let's go ahead and then compile our code. So here we probably might not have to worry about the GCC and all the other flags, right? So with that, but if we ever need to do that, I've already aliased mine to C. So if you see me using C, that is that. So if you like to use all these flags, right? If coming from ALX, right, you may probably want to use it. But GCC, then what we need to do is we want to like compile everything that is of relevance to this, and we are going to be using functions from this file over here. So we need to compile with this file as well. So what we have to do is to do something like gcc driver.c as well as the list operations.c, right? Now that will compile our code for us. But I think maybe it's much better if we rather give it a better name, right? So that at least we can write it out for it. So yeah. So I'll remove the a.out that was gotten, and then let's write our code and see. you can see that everything is working as we expect, right? We're pushing to the list, right? So this looks like in exactly as we expected. So 0, 22, 67, 192, 1, 23, 4, negative 10, 2, and 5, right? And because we're pushing, think of it like the start where we are doing last in first out, or basically every time we are pushing to the head of the list. So like the last item will become the first, right? So that's why this is the case over here. Okay. So now we see that our push function is working all right. But then let's try it in a different way, right? So what I'll do is this, right? Let's work with some let's make it a little bit fun. You would divide the size to by 2, and then what we will do again is we would now also try to use the append, right? So now you say for I is less than
size of 2.
yeah, really not size that we would have to like get the next of the values, right? Like as in this is size divided by 2, right? But then okay, so what we would rather do is this: you say I is equal to size divided by 2. That makes sense, right?
Yeah. Then you'd step backwards, like,
I'm
oh,
stepping
okay.
forward.
Oh, okay. From the okay. Yeah. The index.
Yeah.
Okay.
Then we are going to append to the lists, and then we are going to insert the numbers at I, right? So now that would be what we are going to use, and that is also going to should work fine. So we'll print it on 2 occasions, right? So here we are inserting uh so let's print something here. So after using the push function, right? So I'll add some few stuff here, and then here I would also say after using the append function, all right? And that's that. Okay, so I would also do this. So now let's test this one as well. Let's compile our code. All right, compiles fine. So that, oops, segmentation fault. Okay, our very first error so far. Um, let's work through that and figure out what the issue actually is. Okay, so we
Do you
are
think
getting a segmentation.
the starting of the
Yeah,
second for loop should be like size over 2,
exactly.
right?
Yes. Yeah.
Okay.
So let's use GDB to step through this, right? So
Step
I'll
3.
say GDB,
Cool. Shouldn't
then
you compile it with like okay, go ahead, like with the dash
yeah,
G flag? Okay.
yeah, I would actually do that, but for now, like let's
Okay.
just let's do a normal approach, right?
Okay.
So
First.
yeah,
Okay.
yeah. So now what I'll do is I'll just run it, right?
Okay.
Run it, and then I can see that it occurs during the time where like we are in the append method, right? So if I do a backtrace, don't really get much information. So for now, let's just back out and then rather do the method where we are going to um, compare with the dash d, so that when we use a GDB, for instance, we can get more information on where the error is actually coming from, where like the file where it's occurring inside, the line that is causing the error, and a few other stuff. So let's run again with GDB. I run it, and then I see that the error is coming from when we are setting the tail next to the new node, right?
Hmm.
That seems to be where the issue is coming from. So in VS Code, what I can do is I can press Control key and then press the or tap on the mouse, and then it will take me to the exact place where this is occurring. All right. So now let's try to decipher what is happening. Okay. So here we are setting our node correctly. Okay, wait. Okay, yeah, looks okay. Yeah, setting the node, which sets the data portion as well. We check if it is empty or not. Then that. So this error is actually coming inside over here. That means that when the list was empty, no error occurred. We can at least assume that, or like say that, because this else would only run if this if doesn't match. Okay. So new node. So let's tell next equal to new node is causing a problem, which is a segmentation fault. Let's see what is really happening.
Data.
Let's see. Okay. Let's tell next or to now. Sorry, next node is causing a problem.
Okay.
Okay. Let's see. Okay, so currently okay, let's get back to this place. Let's see. Over here, yeah, I set both to the tail, like to now, right? So
List. Okay.
back to this area. So
This is now
so current when we are inserting out the tail. Okay.
fault.
Okay. So the error that is occurring is a segmentation fault, meaning I'm writing to a place where I'm not allowed to do that. So maybe I'm missing something out. Okay, so let's see something here, right? Since we are going to be appending,
can we print out new node? Sorry, sorry, just a guess. Like, can we like print out new node and list till next, so we can see like which is null, and then like try to look at what's happening there, like the addresses. So with the
okay, so earlier I was saying that I would bring out this over here to the outer side,
oh, okay.
like yeah. But let's also try the method you are saying. So you are saying that we should do something like over here we are, let's say, printing
Yeah,
out what are we
the
printing out?
percent p, the address of list till next, and
Okay, so
yes. So yeah,
um
let's see the description.
till next
Till next,
address.
yes. Address, okay. And then also new node.
All right.
Okay.
Mm, So okay, until next.
Yes.
Oh no.
Till next and new node. Yeah. Okay. Yeah.
Okay. Okay.
Next.
Till next. Well, at the particular point in time, the till next might probably be undefined.
Okay.
So that
Shouldn't
is
it
why
be
I was
none? It's
yeah. So
supposed to be.
that is why I was saying that since we are going to be appending to the list
Okay.
to the list, we can
Mm.
set the
No,
next
no.
to be
Okay.
now outside of any of these two guys, right?
Yeah. Okay. Yeah, that
Because
makes
here
sense.
yeah, because here there's a potential of it becoming now when I'm trying to access it, which could also cause the segmentation fault.
Okay.
So
Okay.
let's get back to this area and then
Let's see if it works now.
one more time. So driver still causing segmentation fault. Amazing. That's great.
Mhm.
Let's dig deeper. Okay.
Okay.
So
So it
we
stops
are
at when after printing 5, right?
yes,
So it goes
yeah,
through the first time, then the second call to the second loop where it's like append. Okay,
yes.
so
That's where
it's not
causing the issue.
the seg fault. Hmm. Okay. So okay, okay.
Um,
Numbers.
probably okay. Okay.
Hmm.
Um,
Wait.
okay. This is nice.
Hmm.
This is nice. Okay. So, one, two,
Okay.
three, four. Okay, hold on. Okay. Uh, one, two, three, four, five. Okay, that's fine. Um, probably the arrow is really glaring at us, and we can see it. I'm probably
Hmm.
sure. Okay. Let's
Hmm.
try
Let's
it
come
again.
back.
So
Yeah.
let's till next. Okay, fine. You know what? Let's rather try this. Let's try the method you were coming up with, where we are going to print out the thing. Right.
The
So
addresses, right? Okay.
yeah. So I have oops, a function like um this function here, which will print out or like would return the last node, or like the value at the tail node, right?
No, okay.
So
Yes.
um yeah,
Okay.
so let's say last node, and then I'm going to print that out. It's a D. Then
Okay.
what is going to
Mm,
bring it?
list.
Uh, yeah. So that is what is going to come up with.
Okay. Oh, okay. You have
And
like
then
last find already. Okay. Okay.
yeah, 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 yeah. So
Okay.
but before that, let's maybe probably let's say comment these out for the moment, this one as well, and rather just call the last method.
Mm.
I keep saying method. Well, I've been working with methods so far, so that's why. Okay, so um, I'll print out the last node, which
Okay.
based on this, we are going to expect that is going to be the last one that was inserted, which is going to be 23, right? So
Okay.
let's compile and try. Segmentation
Hmm.
fault. Okay.
Okay. So it's
Um.
fundamental.
Okay. So
Hmm. After using
probably
push. Okay. Print list. Hmm.
yeah. Okay. So let's
Okay.
comment out this one as well, and then
Let's
see.
see
I
if
mean,
it's enters.
the
Okay.
this
So
let me call it
it's something that has to do with
yeah.
Hmm. What's
Well,
the
I mean,
last?
this lasts doesn't really have anything to do. Okay, so I
Hmm.
think it has to do with the tail.
Okay.
Okay. Anyway, let's also try the um first, right? Let's say
Okay.
what if I try to get the first node? Um,
Hmm.
so in that case, we are going to expect that that's going to give us the
Five.
this one.
23.
No, actually this one,
Okay.
23.
Okay.
So that's the current first, right? At the top
Okay.
of the list.
List.
Okay,
Okay.
let's try that. And that gives us the correct answer,
That
right?
works.
For the
Okay.
23. So we can
Hmm.
see that issue is coming from the tail.
Tail.
Okay,
Hmm.
yeah. So when it is empty,
Hmm.
yeah,
Okay. Tail.
doing that. And
Hmm.
so probably maybe missing out a few stuff. Let's see. We said that when when we have a new node, what's going to happen is we are going to set the tail
Address. Yeah. Tail
to
next.
this, and then
Okay.
the tail will
So
point to the new node.
tail becomes that. Okay.
Okay. So would there be something that we are like maybe missing out that might be causing this to happen? Like
Hmm.
based on our current code
Hmm.
here, we are doing
Hmm.
about the same thing, but probably we are missing out at a particular place.
Okay.
Let's
Can we
see.
see the init function? Just to
Yeah,
confirm.
that's that. That's it.
Okay. Okay. It's there. Set to null. Huh. This is an interesting seg fault, honestly. Okay. Hmm. List. Okay. 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 Can we try printing? Can we try like just accessing the tail part and just printing the address there when we have populated the list, like after populating the list, then we can just like check the tail, the tail pointer, like the address there. We just like
All
print
right.
the address of the tail. I want to know if that's going to lead to a seg fault. If that's leading to a seg fault, then we'll have to
Okay.
rethink it.
Relax. Wait. I'm thinking of something, right? You
Okay.
see, when we push into the list for the first time, right? When
Mm.
we push into the list for the first time,
Ah,
we
we didn't
don't.
set node. Okay. We didn't set the
Yeah,
tail node to new node. True.
exactly. Right. So
Okay.
yeah,
We didn't set the tail address. Yeah, that might
yeah,
be it.
yeah. So here we probably have to just make another check. So if
Mm.
the list size is equal
Mm.
to 0,
There.
then
Then
um,
remove
list
it
tail
till
equal to new node,
equals new node and list head
and list
equals
tail is
new
also
node.
equal to new node.
And then you can move those new nodes stuff up.
Yeah, if there's no that, then we can go ahead and then put these guys um,
Mm.
where they belong. Right.
Okay.
So,
But don't you think the okay, yeah, okay, it's correct. It's perfect.
right. Okay. So now let's come back to this one and let's access the last node as well this time around.
Sorry, mental. Could you go back to that code? Uh, The yes. Do
Yeah.
you think we should have like the new nodes assignment, the data part and the next part like should first be like the data part can be
Exactly. Exactly.
outside,
Yes, yes,
then
yes.
yeah,
Yeah,
and
yeah,
then
yeah, yeah.
next
I
part should be
yeah,
null. So,
yeah.
okay,
Right. Yeah. That's it. Thank you.
okay.
Okay. So
The next the next member, shouldn't it be null first? Or I don't know. Oh, okay.
Um,
Doesn't
yeah,
really matter, right? Okay.
yeah, because we are inserting at the head, and if we say
At the
next
head.
is equal to now, we probably be causing some issues.
All right. That's fine. Nice.
Okay. Let's try. Oops, not that. Compile. Then let's run. Okay.
Uh-huh.
And I getting
Yeah.
something good.
Uh,
Right. So our last node is 5, and we are getting it correctly. Right. So
okay.
in the same case, we can get our first node.
Mm.
Right. Just a very simple oversight could really cause a lot of issues. But yeah,
Mm.
tagging is a very good thing to do. Right. So you can see that now our first node and then our last nodes are printing out correctly.
Correctly. Yeah.
Yeah. So yeah. So now we can bring back our
Our loop. Yeah.
so yeah.
Prince. Okay.
So we are expecting that like after we have inserted this way, right? So this more of like we are always inserting at the beginning of the list. So this one goes in first, this one comes, and then becomes the new first, the new first, the new first, and then the new first, right? But now
Mm.
we are going to append. So now this is going to continue from wherever the last element
Last is,
was.
which is from
Yeah.
5.
So
Okay.
yeah. So if our tail node is working correctly, then the new things are going to continue after this 5 year,
Mm.
right? Because we are appending to the list now. Okay. So now let's go ahead and then do that. So let's bring this to this place where we would actually see the like the first and the last
First and last.
before we. Yes. So now let's compile one more time and test our code. Okay, last
Mm-hmm.
node. Okay, okay.
Yeah, the
We yeah, those kind of things. Let's get rid of that.
mm,
All right. So at least we can confirm that our thing is not causing error. So we can
yeah, it's working.
yeah, you can see that now the 192 and 0 are being appended to the list. All right. So
Mm.
our tail node is working correctly now. So the issue was that we left out the we didn't account for the case when we were
It's
pushing and
empty.
the list was empty to
Mm.
set both of these, right? So Alex,
Yeah.
we've seen some of the caveats when it comes to trying out new methods, right? I've been
Mm.
doing this for a while, but still, it still gets me sometimes. So
Yeah.
uh, I think it's a good practice to also see, and yeah. So you've seen
So it
how
works
this,
both ways for both like the head and the tail. We must check that they are like when we're adding or like pushing or appending, the two cases must, if the list is empty, they must be initialized to the new node. So like the head must be
yeah,
new node and the tail must also be new node.
yeah,
So that's
yeah,
that's clear now.
yeah. So also on our board, I should make that clearer.
Mhm.
Uh, yeah. So let's bring it here. So
Okay.
so um
Inside next and okay, I think that
okay.
should be
Uh,
first. Oh, like there should be like a condition if, and you know.
yeah. So here I'll say let's say a note here. It applies. I'm trying not to do the same thing I'm doing with the code to repeat
Yes,
myself.
so,
So I want to put it
yeah,
here and then tell them that it's the same
makes
thing, right?
sense.
Yeah,
You just
but
have like an arrow pointing to.
yes. Okay. So
Okay.
simple note here. So When the list is empty,
empty.
the head and tail point to the new node.
Okay.
Be sure to check that.
All right.
Um, let's make this a little bigger so that So
Like,
so that's
yeah.
like that. Yeah. So that should do for this. Okay. Yeah.
Mm,
So really work for this one. So at this point, we are not worrying about re-leaking memory or anything of that sort. We work on all of those things. But for today, at least we've been able to see how to use the append and then the push and seeing errors come up and fix it. Right.
mm.
So the
Sorry,
next session is be on Monday,
mentor.
actually.
Sorry.
Yeah.
Speaking on leaking memory and all that, I just have like one question. It's a straight answer. So when do we check for memory leaks? Do we do that after the main implementation, while we're implementing, or you know, is there any like perfect time to start checking for leaks? Like, well, maybe if we malloc now and then along the line we know that we're supposed to free, do we free then, or do we like go through the whole process then start implementing the freeze? Because that gives a lot of headache when you're working on like big projects. It happened in simple shell, it's happening in multi. So when do you think we should be freeing and checking for leaks?
Okay, so for this one, I would take it from the user end, right? Um,
Okay.
so let's say we are using a function that has been provided for us, like the append, the push, and all of those things. We know that they are going to uh, like
Okay, right.
allocate memory, right?
Mm,
And we know that when there's an error, they are going to say that something went wrong, right?
mm,
So um, actually what we can do here, like and like currently in this kind of implementation, we are
mm,
saying that when there's an error, we just tell them that they can't continue,
mm.
and we would allow them to either move or not do something, right? So
Okay.
for this one, in our case, what we have to take note of is that, or what we have to work with is that after we are done with this list, something was allocated for it, so we have to get rid of it.
Okay.
Right. Yeah. So in our case here, we are the people responsible for deallocating whatever the programmer allocated there. Because if he deallocates in his code, we can't even get access to the memories that we are trying to work with. Right.
Mm,
So we have to take care of deallocating the memory. Currently, we don't have any function from the programmer that will take care of this for us. Right.
mm.
So what we have to do is to handle the deallocation ourselves. So
Okay.
that would have been something like we would do, let's say, like we'll have a method that is going to remove everything from the list for us.
Mm,
Right.
mm. Okay.
Yeah. So for here, we would have been in charge of that. But let's
Mm,
say you are working with the function which is supposed to, let's say, do something like,
mm,
uh, let's say we wanted to do something particularly about when they were trying to allocate memory and then something goes wrong and you want to
mm,
exit out of the function or exit the program entirely. What we
mm.
have to do is we have to be responsible for the deallocation of the memory because we want to quit them out of the program entirely. So
Okay.
what we have to cover here is would have been that when this node allocation fail, then we have to
Mhm.
clean up before we exit out of the program, right?
Okay. Mm,
Yeah. So the thing is that when you allocate memory in the place where you use it, you allocate it over there,
mm.
right? So you can allocate memory, and then someone else will have to use the memory you allocated. They are going to be in charge of the deallocation.
The allocation. Okay.
Yeah.
Okay.
So basically, whenever you use a memory allocated uh, structure, you have to be responsible for the freeing of it. Right?
Okay.
Just like how when we use the string do
String do.
function, we have
Yeah. It was
that.
particularly meant for our use, and we had to like
Yeah,
deallocate it
yeah,
because no one else is going to use the string do. It's not available for anyone to like access what's there, and we were done with it, so we could just deallocate it. So if I get you
yeah,
correctly, basically when we had to deallocate is one when we are done using memory that we allocated for our use as programmers, like while we're programming, to perform operations. Then also when we have like an exit situation, when we need to clean up the whole memory allocated, that's nobody cares if anybody wants to use anything. We just need to like deallocate all the memory since we're exiting the program. That's another case. Then when we can not deallocate, like when we don't need to deallocate, is when the program is still going to be in use, like the memory allocated is still going to be used somewhere. Someone can still like do a push, someone can still want to print stuff that is in the memory allocated, so we leave the memory there and then move on, right?
yeah, sure.
Okay, thank you. That explains a lot.
Sure. Yeah. So in the next session, we are going to like implement the pop method, and then the print element at
Okay,
function,
function.
which is going
Okay.
to take care of popping stuff up, right? So this is when we are going to start talking about memory stuff, like handling memory deallocation and a few things. And then from there, we're also going to write a bigger function, which is going to pop everything off the list. Okay, like we
Yes.
remove everything from the list, right? Yeah.
Mm,
I'm tempted to say stack, but
mm,
we'll get there. Right? So
yeah.
that's what's going to come up. Right?
Mm,
But then we can see that so far our append methods and our push methods are all using constant time operation, meaning that we are doing it in a finite number of steps. We are not
mm,
doing it based on the size of the input of our list.
mm,
Right. So normally we would have done while temp is or like whatever thing that you have. Let's say you would say while the node next, or let's not use node. Let's say while current next is not equal to now, you
mm.
move all the way to the end, then
And
you insert. Yeah,
mm,
but that's not very efficient. So now to test whether our list size function is sorry our size um, um our list like what do I say? Our size
mm.
member is actually working. So currently we have 10
Okay.
elements, right? So let's just confirm whether um, we actually
Okay.
have 10 elements. So let's
We just
print
print
printf uh, um,
percent D.
size of
Okay.
lists.
Okay.
And
And
that
then
is going to be list size,
list size. Okay.
right? So now let's compile one more time. Oops. Okay, it is a size T.
Size
So
T. Okay. So
yeah,
LD. Okay.
actually, yeah.
Okay.
Okay, so let's
Mm.
run that. Okay, and you can see that
Okay.
it's looking fine. So here we actually got this in constant time as well.
Mm. Mm.
So
Yeah,
we
that's
didn't
true. You don't have to like
get
go iterating and then counting. We've
yeah
been keeping track of it, so it's there
exactly
in the okay.
yeah yeah.
All
So
right.
as we go through, we'll be like updating this list structure to handle a few things, right?
Other things, okay.
Yeah,
Like error
which
codes now, right? Or return values or something.
yeah
Like
probably
yeah.
we can add a few things over there as well, right?
Mm,
So currently you can see that our first and last macro functions are also working well, right? So these are too small for us to write a full-blown function for. So that's why I normally like to use the macro functions for them. So, but then if you like to use actual functions, that's also fine. But these things work well and they are simple to build. Okay, so
Sorry, when you say like a full-blown function, how else could you write this? I mean, this looks perfect. How else do we write the first or last function? Is there
well,
like
you could do something like first
okay,
go to list T
list
over here,
T, okay,
right? Then you would return um, list T
list
head
with
data,
data,
something like that. Right?
gross,
So we could have done something like this, right? But I
okay.
mean,
Yeah,
just 3 lines.
it's grotesque looking at. I mean, from where you have the macros and then looking at that, it's like who really wants to do that? I know, right? Like, yeah,
Yeah, but I
that's
mean, yeah, yeah. So
yeah.
it's really maybe
Uh, is this my internet? Mentor Max, we can't really hear you. Uh, okay. I'm sure this is not from my end. Mentor Max.
I think.
Something's up. Okay, okay. I just heard you now. Like, yeah. Okay.
Sorry, a call came
Okay.
through. All right, sorry
Oh,
about that.
okay.
Yeah.
Yeah, no problem.
Okay. So yeah. So you were saying something before the network was off.
Oh, no, I was just like saying that looking at this like macro definition, like it's I just can't like think about any reason why anybody is going to like do it in that way that you showed me just now, like the return style. Like this is obviously better. So that was just what I was saying, basically. It's like
Yeah, and also probably also comes with like being lazy as well, and then yeah, if you are that as well, yeah.
mm-hmm.
So it's I mean, if I didn't know about macros, I'll probably also write a full function for this,
Yeah,
right? But I mean,
this is
yeah, yeah. But I mean, so someone could also say that they could write a function like this, where they would say something like first, um, then they'll give it the listy
let's see.
list, oops, stay list, and
Hmm.
then oops, right on the same line, they'll say return lists, uh,
Hmm.
uh, list head
Yes.
data.
Hmm.
But then since I'm on VS Code, it would
It's automatically
automatically.
linked to it.
Yeah,
Yeah,
so
I mean the
someone could
macros
also
are
say that. Yeah,
they're the best.
yeah,
I'll definitely do
okay,
it in the macros. Yeah.
yeah. So I'll end the session on this notes. Then in the next sessions, you are going to be building the pop and then the print
Print
element
element
art.
art.
Then
Okay.
we could also use that as a chance to discuss more about memory stuff. Like most of
Mm.
the things for that day is going to be about deallocating memory and then ensuring that we are not leaking memory when
Mm.
the time.
Is
Yeah.
this tomorrow?
Now that'll be Monday. The
Okay.
sessions are held Monday to Friday. Yeah.
Okay. Okay. Okay.
Yeah.
Can't wait.
So
Yeah.
sure.
All
All right.
right. Thanks so much, mentor. This has been
Sure.
very enlightening.